Good afternoon. Still we have 2 minutes. Before we start today's lecture, I'd like to accept questions from you guys. Actually, up to the last week, and we discussed the most of the fundamental informations, and then the solution strategies to various mechanical systems. So although we discussed those stuffs for unidirectional, one-dimensional problems, but the basic principle is exactly the same for multiple dimensions too. Okay. And what is the benefit of talking about one-dimensional problem? Talking about one-dimensional problem provides us many, insight to actual, much more complicated problems like in 3 dimensions. So what is important in the discussion of one-dimensional problem is we can, using the 3 conditions that I discussed, that I introduced you using my diagram, so-called this diagram. Using those 3 conditions, we can approach to any kinds of mechanical problems in a same consistent way to solve those problems, okay? You don't have to worry about other approaches depending on the problem types as given in many textbooks, okay? So if you look at, if you read other textbooks, including the current textbook, they propose, the authors propose different approaches depending on the types of problems. But as I emphasize, you guys, you don't have to do that. So the approach to the solution is always same, okay? So if your condition is complicated, then you can introduce some kind of assumptions or simplifications to your approach, okay? That's it. But as long as you are talking about linear elasticity, especially in the linear elasticity, you don't have to worry about any kinds of assumption, okay? The solution strategy is really straightforward. And the last time that we also discussed so-called principle of superposition. The reason that we can use principle of superposition is because we are using the linear elasticity. So whenever we use linear elasticity, or mathematically speaking, if we have a linear system, then we can superpose different problems to obtain the final solutions. That's how we can decompose the problems, or I mean, especially when we talk about statically indeterminate structures. We decompose the structural condition into many small units of the structural systems. Those are statically determinate. So we can determine the stress and displacement by using only the equilibrium condition. And after finishing all the calculations, we just superpose all the responses together to obtain the final response, and we impose the conditions for the boundaries to check or to find out unknown reactions. Because our structural response would be proportional to the magnitude of the reaction. So we can determine the reaction such that a certain point where we have displacement boundary condition can satisfy actual displacement condition. For example, if one side is fixed, then displacement at that point should be equal to 0. Say, because we decompose the problems into many multiple units, in some units we have, say, positive displacement at the boundary, at the position of the boundary, and then in some the other subsystems we have negative displacement. And then if you add up, or if you superpose all the displacement, and then to satisfy the boundary conditions, the displacement at that point should be equal to 0, isn't it right? That's how we can check the reaction for statically indeterminate structures. So if you don't like such kind of superposition principle, then you don't have to do that actually. Just prescribe the displacement field and identify unknown displacement, and then you calculate strain, and then after calculating strain, then you calculate corresponding stress. Of course, strains are given in terms of displacement. Stress also should be given in terms of unknown nodal displacement. And then finally, you check the force equilibrium to finish your problem. Okay, the solution procedure is always so simple. Actually, last time I got a question from Jusunghi, and he tried to do homework problems probably. And his question is about one-dimensional problem, and he consider a one-dimensional bar, and then the temperature of this one-dimensional bar increases by delta T. That because the temperature increase, and then as temperature goes up, then this guy, the overall structure would expand like this because of thermal expansion coefficient, isn't it right? This is thermal expansion. But here there is an interesting point that, so we have a spring here. Initially, the spring is not contact with the structural part. There is a gap S. So this problem is not, what is important regarding this problem is, this problem is not linear. Oh, sorry. Okay, this is important to understand this problem. So first, that what we have to consider is first, the temperature increases, and then the end of this part, so moves toward the end of the spring. Okay, so we have to divide the problem into two different stages. In the first stage, we have a member, and then the end should grow to the end of the spring by S. Okay, by S. Then you can calculate the elongation of the first part and the second part, isn't it? So here the elongation of the first part is, how do you calculate this? Let's say this is a L1 or L2, and the elongation of N1 is alpha delta t. Let's say I want to call this the series 1, and then length L1, and then delta 2 is, if the material is the same expansion coefficient, 1 and L2. That's how you can calculate the elongation of each part. And then the total elongation is equal to L delta 1 and delta 2. So until this delta is equal to S spacing, this is the series 1, okay? Once this end point touches to the end of spring, then we have new problem, okay? We have new problem. Then because this part is touches, now touches here, then the further increase of temperature would produce reactions here, non-zero reactions. So make sure that here the reaction is equal to 0, because this is free expansion. The free expansion means there is no reaction development and there is no stress development. Okay, so here there is no stress development. So no stress means no internal force. Okay, so no internal forces means no reactions. Is it clear? So to approach this problem, so we have force equilibrium, stress and strain and displacement, isn't it, right? This is our solution procedure here. And to use constitutive model here, we have to define the mechanical strain, isn't it, right? And how do you define the mechanical strain here? So our mechanical strain, epsilon, the mechanical strain for the calculation of stress is the total strain, so minus the thermal strain, so alpha, and then delta t, isn't it? Delta t, but make sure that, so we increase the temperature from this point, isn't it, right? So the strain which produce the stress is what? The total temperature increase minus the temperature increase corresponding to the end of the series 1. Is it clear? Okay, that's what you have to consider to calculate stress field. You understand? Okay, today let's talk about torsion. So here we have today's subject, torsion. So we have learning objectives here. Say first we wanna talk about the twisting of circular bars and then hollow shaft activated by the torsional moment. Now what is important is what we discuss here is only applied to circular cross section. So only for circular cross sections. So I will explain you the reason later, okay? And then we're gonna develop so-called torsion formula, and then also we wanna discuss how to calculate the related shear stress field depending on the radial distance measured from the center of the cross section. And then using this torsion formula, we want to derive so-called torque displacement relation. And then we'll calculate whether we have the normal and shear stress components on inclined sections of the circular shaft. And then here we'd like to talk about the relation between the elastic modulus and the shear modulus. Okay, whether if these two moduluses are independent or not. Okay, we're gonna check it. This is called shear modulus, and then this is called elastic modulus. So another name of elastic modulus is we call Young's modulus. Okay, so make sure that for the normal stress component, we have the normal stress is given by the elastic modulus times the strain. Okay, and then the shear stress is given by the shear modulus times engineering shear strain. Actually, this is a linear elastic constitutive law, but what is important that you need to keep in mind is the original form of Hooke's law is not given in this way. The original form is given in this way. The strain is equal to the strain caused by the stress is equal to stress divided by elastic modulus. Okay, so if you understand this is strain caused by the stress, and then we can superpose the strain caused by the temperature too. Okay, so alpha delta T, this is strain caused by the temperature. And then if you want, you can add up, say, strain caused by humidity, delta H. Here the H stands for the humidity. Delta H means the change of humidity. Okay, and then here the kappa, this guy is called epsilon, the strain caused by the humidity. In the case of concrete, we call it drying shrinkage. And here kappa is called dilatation coefficient. Kappa is called dilatation coefficient. Okay, so alpha is thermal expansion coefficient or thermal dilatation coefficient. So alpha is called thermal expansion coefficient or thermal dilatation coefficient. Any question? Okay, so that's what we're gonna discuss in this chapter. So then the first is the introduction part. Okay, let's talk about cases where we have torsional moments. Okay, so first let's consider a bar, and then if you imagine two bars. Okay, two bars are attached to this one-dimensional structure. One is in horizontal, the other one is in the vertical direction. But we applied coupled forces to two opposite directions. And the first one is in the vertical direction, and second one horizontal directions. But if you check the force equilibrium in the horizontal direction, obviously it is equal to 0, isn't it right? For example, for this guy, this is equal to P1 minus P1. It is equal to 0. Obviously, it is trivial calculation. How about the force in the vertical direction? It is also equal to 0 because for this P2 minus P2 is equal to 0. Okay, so if you check the force equilibrium only in the horizontal or vertical directions, they are equal to 0. So we can say that the force equilibrium condition is beautifully satisfied, so that we don't have to worry about. But here, if you calculate moment, with respect to the center of the cross section, then we have non-zero moment, isn't it right? For this guy, we have what? T2 times P2. So we have non-zero moment. And how about for this guy? This guy also produced D1 times P1. These two produce non-zero moment. And how about let's check the direction of non-zero moment. Here, non-zero moment is the same as the longitudinal direction of the member. Okay. same as the longitudinal direction of the member, then we call this moment especially torsional moment. Is it clear? This is the definition of torsional moment. So we have moment, but the direction of moment is the same as a longitudinal direction of the member. Then we call it torsional moment. And then here how we represent torsional moment. Actually, torsional moment is also kind of vector. But to indicate this is the moment, so we use double-headed arrow. Okay, so we use right-hand rule. You know what's what's right-handed rule? So this is a positive direction. Okay, so if you have moment rotation in this way, then we want to consider the thumb direction is default the positive direction of the torsional moment. Is it clear? Okay, this is a right-hand rule. Or if you don't like to use double-headed arrow, instead of using double-headed arrow, you use circular arrow too. So it's okay. The direction of circular arrow indicates direction of my 4 fingers, except my thumb. Okay, this is positive direction. Is it clear? Okay. So which one do you like? Actually, for me, this is better, okay, because I can recognize the direction more clearly. So we can use the vector sign convention. So once we introduce a coordinate set and we choose this is default positive, so let's check T1 and T2. So if you want to use this coordinate, which one is positive, T1 or T2? Is T1 is positive or T2 is positive? So make sure that those arrows indicate the actual direction of my vector, but it doesn't determine the sign of the torsional moment. The sign of torsional moment, what I mean, the magnitude of torsional moment should be determined by the choice of coordinate system. So which one is positive, T1 or T2? T2, good. Okay, so this is a vector representation, okay, because we want to choose, this is our choice, so we want to choose this direction is positive, that's why T2 is positive. Okay, alright, so another name of torsional moment is also torque, same thing. Okay, the moment that produces the twisting of bar and shaft we call torque, torsional moment. Equivalent torque. Any questions? Again, we want to use exactly same solution strategy. So we'd like to assume the deformation field, and then we want to calculate corresponding strain field and the stress and the calculation of force. That's what we want to do. So please keep in mind this approach. Okay, so now I want to define my deformation field. So let's imagine I have a member. This member first, okay, so forget about torsional moment. Okay, actually, because I scanned the textbook, that's why we have the torsion moment here. But what we want to discuss here is, so we have twist, some twist deformation. That's what we have now. So let's do not talk about what causes this twisting action. Anyway, so we have some twisting moment, so twisting deformation. Okay, let's say I have this twisting deformation, and then if you look at this twisting deformation, and then say this is the original line. Let's say I want to draw a line on the surface of circular member, so P and Q, and then after deformation, this line PQ is displaced to new point PQ prime. Okay, PQ prime. So you may imagine another configuration. Let's say I have a circular bar, and then this is the original line, P and Q. And then maybe this point is displayed into here, like this. So P prime and Q prime. But if you understand there is a certain point that, you know, parallel movement, then the overall member is rotated by same amount of rotation on the P side and Q side. But that doesn't produce any strain, isn't it? So this part is correspond to rigid body motion. Okay, that's why we subtract this part. Okay, if you remove this part, so we have only meaning for displacement. That's why we want to consider this configuration. Is it clear? Okay. Then we can measure that displacement from Q to Q prime. Here, Q to Q prime. Then how do you measure this? So we can measure, let's say, initially I have a circular section. So initially we have Q, and then the point Q is displaced to new position, so Q prime. Now obviously there should be angle change, isn't it, right? So we want to call this angle change, we want to denote this angle change pi, phi. And then the radius is, if you denote the radius, is equal to r. And then the length of displacement, how do you calculate the length of displacement? The length of displacement is measured by what? How much is it? This is equal to r times phi. Okay, r times phi. Okay, look, so if you look at this reference line, this reference line is deformed to new line. Okay, new line. So which means we have certain shear strain, isn't it, right? So this guy deforms the end point. Let's consider we have P and Q, and this new Q point is displayed into here, so Q prime. So according to the definition of shear strain, this is shear strain, isn't it, right? That displacement is equal to the radius times phi, and then this is shear strain gamma on the surface. Then how do you calculate the shear strain? The gamma is what? The displacement is radius times phi, r phi, and then it should be divided by the length of the member, L. Okay, this is a shear strain caused by the rotation of this circular bar. But look at the center. If you look at the center of the cross section, the center, there is no change in the center, which means my shear strain, the measurement of shear strain must depend on the radius, isn't it, right? So we must have the shear strain value maximum on the surface. This is the maximum shear strain. You understand? This is the maximum shear strain. So I want to measure the deformation by angle of twist. Phi is angle of twist. And then once we have angle of twist, then we can measure the maximum shear strain. Okay, so here now let's consider counterpart in our uniaxial problem. In the case of a uniaxial problem, the angle of twist corresponds to elongation, and then that shear strain corresponds to the normal strain. Is it clear, right? Okay, so now let's check the change of shear strain. So as I told you, the shear strain is maximum on the surface of the section. So we can consider proportional relation. So we have maximum shear strain on the surface measured by radius r. And then of course my shear strain should be determined by the radius. So here rho is the radius. So rho is the radius. So arbitrary position. This is rho. So for an arbitrary position, the shear strain, if you move rho to the left hand side and rearrange this equation, this is given by rho divided by the radius of the section times the maximum shear strain. So how do you calculate the maximum shear strain? So maximum shear strain is here, right? So this is equal to rho times rho divided by r times r phi and then L. It cancels. This is equal to rho phi divided by the length of the member. Okay? So make sure that, as I told you, so we are talking about the displacement compatibility. For example, when you talk about force and stress and strain and displacement field. So what happened here? Okay, what happened here? What happened here has nothing to do with any stress condition. Okay, so purely displacement and then dimensions. So even if you consider the circular section, so hollow section, in this hollow section, depending on the position, we can calculate the minimum shear strain and the maximum shear strain, because the shear strain is given by the geometric information. So instead of rho, so we measure the inner radius r1, and instead of rho, we put the outer radius r2, measure maximum shear strain. Okay, so then what do we have to do? We just discussed we just define the displacement field, and then we discussed how to calculate the strain. Here the strain, instead of strain epsilon, so we have to deal with the engineering shear strain. Okay, so if you don't like to use the epsilon for your strain description, let's use gamma. Okay, engineering shear strain, and the corresponding stress is shear stress tau. This is given by the Hooke's law for the shear strain and shear stress. Okay, that's why we have to talk about the Hooke's law for the shear strain and shear stress here. So the approach is really sequential. To calculate shear stress, we have to consider this equation. So instead of engineering shear strain, so we just put this value here. Okay, so let's try to calculate this value. Then shear modulus times rho p divided by L. That's it. Okay. Then how about the maximum shear stress? The maximum shear stress is shear modulus times the length doesn't change of the member, and angle of twist is the same. Instead of rho, we use the outer radius. Okay, actually you don't have to memorize this equation. So once you understand the procedure of the solution, then we can obtain these equations by sequential consideration of displacement, strain, and stress. So now we finish it up to here. Okay, we did up to here. Is it clear? Then what's the next? The next step is we need to consider the force part. Look, so what force that we have to talk about? So when we define the displacement field, we consider the angle of twist, isn't it right? Some kind of rotation. So if you want to discuss the corresponding force, then what we have to consider as the force? So do we have to consider just translation force like Fx and Fy? Then what component that we have to consider as the force for this problem? Do you remember I emphasized you several times that we need to consider the energy pair always, right? So please consider what kind of energy pair is appropriate. So look at this for this level. So I told you that this level is what? This level is material point level. So the energy ensemble for the stress, sigma normal stress, is equal to normal strain. And the energy ensemble for the shear stress is what? The shear strain, okay? The shear stress produces energy over the shear strain. And normal stress produces energy, or it does a work over the normal strain. Alright, now because we describe the deformation field by rotation, then what produces work over the rotation? Let's check the unit of rotation. So if you check the unit of rotation is, how do you measure this? The unit of rotation is, we can measure rotation by two different ways. So we can measure degrees, right? And also we can measure radian. So radian doesn't have unit, and this guy also too. So basically for engineering calculation we use radian. It doesn't have unit. So which means the force, the measurement of force is what? The unit of the force that we have to consider for this problem must be the same as the unit of energy. And what's the unit of energy? Unit of energy is, for example, we use joule. The joule is what? Joule is Newton times meters, isn't it right? This is unit of energy. So we have to, the unit of the force that we have to consider for this problem should be the same as unit of energy. Then for the unit of this force, okay, for unit of this force, this force, so we need to have the same, unit as the energy, for example. So we need to have Newton times meters, for example. So what is the unit for? This unit is what? This is a unit for the moment, isn't it right? This is unit for moment. Okay, unit for moment. You understand? Okay, so we can discuss the problem for the unit match problem. Okay, then we can easily can get the clue for the proper choice of the force. Any questions? Is it clear? Okay, so now using the shear stress here, so I want to obtain the information of torsional moment. Okay, so let's look at the cross section. So if you look at the cross section, if you observe what happened on the surface, okay, let's check on the surface. And we need to, if you look at the surface, we have shear stress on each point of this surface, isn't it right? And then the shear stress acting over a small area produce a force tangential to the cross section, and then this force must produce torsional moment with respect to the center of the cross section. So let's try to calculate the small torsional moment. The small torsional moment is produced by the shear stress, okay? The shear stress acting over the cross section, isn't it right? And what is the arm length? The arm length is rho, okay? So arm length is rho. Now let's plug the information of shear stress. Where is it? The information of shear stress is here, right? So let's plug in, and then the shear stress can be recast in terms of the maximum shear stress. Then we can obtain this equation. Now, because we calculate the torsional moment caused by the shear stress acting over this small area, and to calculate the final torsion moment, we need to add up all the contributions. That's why we need to take integration. That's why we have this integration. So I'd like to sum up all the small torsional moment. Now finally, we can calculate torsional moment in this way. Okay? And then we have some integration here. So if you look at the structure of integration carefully, rho square dA. So let's use Pythagorean theorem. So if you use Pythagorean theorem, the rho square is equal to x square plus y square dA. Okay? And then that can be expanded further. The area integration for x square dA plus the area integration for, the y square dA. Now what is this? This is second moment of inertia. Second moment of inertia with respect to x-axis. Okay? And this is what? The second moment of inertia for the y-axis. So we are going to call this the polar moment of inertia, IP. In 우리말, 극관성 moment. Okay? So polar moment of inertia is mathematically simply given by sum of the second moment of inertia for two axes. And this is very important to memorize. You'd better memorize this equation. Okay? This is definition of polar moment of inertia. Okay, then so once we have the information of shear torsional moment, so now we have torsional moment. So the torsional moment is given by, my torsional moment is maximum shear stress divided by the radius of cross section times the polar moment of inertia. Okay, so this is called torsion formula. Alright, then let's go back to the information here. So maximum shear stress is given by this equation. So instead of the maximum shear stress, so we'd like to put it here. This is what? Shear modulus G and the radius divided by the length and the angle of twist times IP. By the way, I forgot 1 over R. It cancels. So finally, I have this. So torsional moment is equal to shear modulus and the angle of twist. Sorry about it. Sorry about it. So torsional moment is equal to shear modulus times polar moment of inertia divided by the length of the member times angle of twist. Okay, let's compare this equation with what we obtained for the one-dimensional problem. So initial, what I mean here, the internal force is equal to elastic modulus times what? Cross-section area times the length of the member times elongation. Okay, so the internal force corresponds to internal torsional moment, and the elongation corresponds to the angle of twist. This is elongation, and this is angle of twist, and this is internal force. We call it internal force. And then this is, say, in our textbook there is no clear description about whether it's internal or external, but make sure that this is internal. Okay, internal torsional moment. Okay, this is important to understand the nature of T. You understand? This is internal. Okay, internal. And then this is elastic modulus, and this is shear modulus, and this is a cross-sectional area which has the geometric information of the cross-section, and this is the polar moment of inertia, and that also has the geometric information of the cross-section. Is it clear, right? And then this guy is called what? Stiffness. Similar to this. And this part is also stiffness. Okay? Any questions? Look, so to derive this equation, what I'd like to emphasize is to derive this equation, so we used, the displacement field, we define displacement field, and then we calculate the shear strain, and then we calculate corresponding shear stress, and then we calculate the torsional moment. Okay, by the way, instead of this displacement field, I'd like to say that phi, angle of twist. Is it clear? So one by one. That's what we did. So once I have this formula, then we can use shortcut information to approach our problem. So we don't have to step down into the material point. To obtain this equation, so we consider that we step down to the material point. Alright, so I already explained you the torsional formula, so maybe I can skip it over. And then this is how we can calculate the polar moment of inertia of the cross section. Alright, so it would be interesting to calculate the calculation of polar moment of inertia. Let's say I have a cross section. Probably, I think you already discussed how to calculate the polar moment of inertia in engineering mechanics class, 공업역학 시간. Isn't it right? Okay, so let's consider I have a small segment, small area, and then this small area, so this is dA. And then the angle is, I want to call this is the phi, for example, dp. And then here the radius is equal to rho. Okay, then how do you calculate dA? dA is equal to what? The length is equal to d rho, isn't it right? D rho. And then this is, we can approximate as a rectangle, is the phi is very small, and then this is equal to what? Width times height, isn't it right? This is the area of a rectangle. The here width is what? The width is rho times d phi. And how about the height of the section? Height is d rho. Is it clear, right? Actually, you can consider, a small difference because this is not real rectangle, but this is second order small. Okay, although if you consider small change, a small difference at this point, if you want, we can try. So we have d phi and d phi. Okay, very small. So let's try to integrate this. So we have polar moment of inertia is Ip is equal to integration of rho square and then t p sorry about it, dA here, and this is equal to, dA is changed to d phi times d rho, isn't it? It becomes double integration. So our integration for phi is from 0 to 2 pi, and then integration for the radius is from 0 to radius r. Okay, so let's separate this integration. So this is 2 pi 0 and then d phi, and then 0 to r, the rho square d rho, and this is equal to 2 pi. And that integration is what? That integration is equal to, by the way, rho square and dA. And I made a mistake. By the way, dA is rho times d phi and d rho. Yes, Sogo, you're right. Should be 3. Sorry, d square, sorry. And then because dA already has rho, so d3. Sorry about it. Thank you. Yes, you're right. And then this is equal to integration of rho to the power of 3 is equal to a force of rho force 0 to r, and this is equal to it is cancels pi over 2 and then r force. So typically we use diameter in many engineering applications, but I mean in engineering practice it is customary, to use diameter instead of radius. So if you use the information of diameter, it becomes pi over 32 and then the diameter to the power 4. This is polar moment of inertia for the circular section. Then how do you calculate the polar moment of inertia for a hollow section? Let's say we have two cross sections and then we have outer diameter. The outer diameter is equal to d2. The inner diameter is equal to d1. Then how do you calculate the polar moment of inertia for this section? What do you do? How do you calculate the polar moment of inertia for this blue section? So make sure that the calculation of polar moment of inertia is nothing but just with the calculation of an integration. Okay, integration. The integration means summation. Okay, summation. So we can sometimes we have positive or sometimes we have negative area, which means we calculate the integration for whole solid section. Okay, whole solid section, and then we consider negative integration for this part. You understand? So which means the calculation of polar moment of inertia for this hollow section is very easy. We calculate polar moment of inertia for the whole section. Ip is equal to pi over 32, the outer diameter to the power of 4. And then we consider the red part, minus d1, 4. It's so easy, right? So please understand the physical meaning of polar moment of inertia. Then everything becomes really straightforward. Do you have any questions? Okay, so here I already explained you the nature of this equation, so I can skip it, right? All right, here the shear modulus times polar moment of inertia divided by the length is called torsional stiffness. Stiffness for the torsional behavior, torsional stiffness. And then the inverse of that coefficient, what I mean, 1 over the stiffness. 1 over stiffness is called flexibility. So L over shear modulus and polar moment of inertia is called torsional flexibility. Okay? And then I just explain you how to calculate the polar moment of inertia for a tubular section, isn't it? Yeah? Tubular. This is what I explain you here. And if you have a really thin section, for example, let's say D1 is very close to D2, then in that case we can simplify the formula for the polar moment of inertia by using this equation. Now, for instance, how to derive this? For example, let's say D1 is equal to D2 minus 2 thickness, 2 of thickness, isn't it right? So we can use this. Say IP is equal to pi over 32 and the T2 false. So here I want to use just the reference diameter. So if we want to use reference diameter, we can drop T2. Okay, just the reference diameter. And the minus, and then D minus 2T false, isn't it right? So I wanna take out the false. So pi over 32 the false. Then I have 1, so minus, and then 1 minus 2 times T over D. Yeah, and the false. So if you simplify this, T over D is very small compared to 1. That's why we can obtain this expression. Okay, derive this expression in your place. So for example, this is equal to 1 minus 1 minus 4 T over D, and then plus 4T D square of square. So we can drop this is equal to 0, this cancelled, and we have only this term. Okay, this second root small. Okay, the similar to one-dimensional problem, so let's consider non-uniform torsion. Say we have multiple cross sections, or even if we have the same prismatic section, but we have multiple external torsional moment. Okay, let's consider this situation. So before we talk about this subject, so I want to take, let's say, the 15 minutes break. So if you have any questions, you are very welcome. 준구, shear stress is caused by the torsional moment. Shear stress force. No, Jungkook. Shear stress is always caused by the shear strain. Okay, shear strain. Stress is caused by strain. Okay, stress is caused by strain. So you can get the shear stress by using the force equilibrium. But in the case of torsional, such kind of torsion problem, look at this. So if you have cross section, so we have shear stress in all the directions, okay? So it is very difficult to handle. For example, okay, let's draw a diagram here. So if I draw a diagram, so if you can, in this cross section, for especially for torsional problem, the direction of shear stress is changing like this. Okay, so although, for example, if you want to introduce a coordinate system x and y, okay, the coordinate direction is fixed, but my shear stress is changing its directions. Okay, so it is not that easy to handle the shear stress as is. And also Jungu. The twisting caused by the shear strain is caused by twisting. No, the strain is caused. Look at the flow. It's always saying. For example, say I have twisting deformation. Okay, twisting deformation. So look at these twisting deformations. What you have to be careful is when you talk about twisting deformation, it has nothing to do with torsional moment. So this is just for motion. Okay, this is just for motion. So once I have twisting deformation, so we must have corresponding shear strain. Okay, and then if you have the shear strain, that produces shear stress, and then we have shear stress, and if you integrate the shear stress, and that produces torsional moment. Or you can start from here. Say you have torsional moment, then we can estimate some distribution of shear stress, and for each material point, and then we can calculate the corresponding shear strain, and then for given shear strain we can define a twisting deformation. And then look at this. These two parts, okay, these two parts, please make sure that these two parts, they are independent, okay? They are independent. Like 태극 같은 거. Okay, they are independent. Okay, they are independent. Then what is connecting these two? These two are connected by this constitutive equation. So when you consider twisting deformation, okay, twisting deformation, do not consider the twisting moment. So the way of our textbook is really confusing, okay? So if you consider twisting deformation, twisting moment at the same time, that causes many problems. Don't do that. It's not a good habit. So when you consider torsional moment, do not consider the torsional deformation. Don't do that, okay? You understand? Actually, the analogy to tagguk is my first time to explain, those stuff in this way. Maybe I found it's a really good analogy. Okay, it's like a tagguk. Okay. For example, here. They are independent, but they work together, okay? They are independent, but they work together by constitutive equation, material model. Here we have force and stress. Here we have displacement and strain. And on this edge, we have stress and strain. Okay? You understand? It's really awesome. Okay, so now let's talk about non-uniform torsion. Non-uniform torsion problem. Look, the solution strategy is always same. So we want to use the same solution strategy. So we have the general displacement field. We have general displacement field, and then I have strain, and then stress, and then internal forces. That's what we have to talk about. But instead of stepping down into the material point, so we can use the member information, kind of shortcut. So in the case of one-dimensional problem, this is elongation and the internal forces. Is it right? So actually we have to step down into the material point. Okay, but instead of doing that, so we can just visit to the member level, the elongation and the internal forces and the external forces to check the force equilibrium. So we are going to do the same thing here. So here we just defined and how do you measure the deformation of the member. So here for this torsional problem, so we want to measure the deformation of member by angle of twist phi, and then internal torsional moment. Okay, isn't it right? So let's imagine a member here. Then I have segment 1 and segment 2. Yeah, second segment. Second segment and the third segment. So for this problem, so we can consider total angle of twist. Total angle of twist is equal to the angle of twist measured in the first segment, and angle of twist measured in the second segment, angle of twist measured in the third segment. That's what we can do. So we already have the formula, right? We already have the formula. The individual angle of twist can be calculated by the geometrical or material information of segment I, and then we need to consider torsional moment acting in this segment. So make sure that this guy is external or internal. Is this external or internal? External or internal? Is this external or internal? Internal. Good. Okay. So please be careful. This is the internal. So in the case of unidirectional problems, it was very clear that because we use two different notations, F and then the internal force N. But here in our textbook, it is not clear. It uses just torsion moment T. Okay, so it is rather confusing. But If you take my lecture, you probably understand the meaning of this guy. This is internal, okay? Good, very good. And for the non-uniform torsion, so if you have a smooth surface, the smooth surface again, smooth surface is extension of multiple cross sections because it's changing smoothly instead of summation. So we change it by integration. Okay. So please understand, there's no difference between summation and integration. Okay, they are same, right? And then even for the case that we have change of external forces, so make sure that this is external torsional moment. Okay, this is external, but this is what? TA, TB, is this external or internal? External or internal? Internal. Good, very good. Okay, so now let's talk about the shear stress and strain. Well, before we move into the calculation of stress and strain, I'd like to discuss example first. Okay, say I have a member, I have a bar here, and then I have bar, and then we have point A and point B, point C, and point D, and the E here. And then first, if you look at point B, we have torsional moment T1, and then point C, we have what T1, and then T2 in this direction. Okay, and then again we have T3 at point D, T3. Alright, so let's simplify this problem in this way. I have a one-dimensional member, and then I have a support here, and at point B, A, B, C, and D, and I have here T1, and then I have T2, T3. So they are external forces. So here we have the length is LBC and the LCD. Okay, so first I want to check the force equilibrium. So if we want to check the force equilibrium, first we have to introduce a coordinate system. So I want to call this as positive axis. So sum of all the torsional moment in this direction should be equal to 0. Say T1, and according to the choice of this coordinate direction, the sign of T2 is minus, and then T3. So here, given here, T1 is equal to 275 Newton meters, and T2 is equal to what, 450. T3 is equal to 175. So if you compare, if you check all these numbers, this is equal to 0. Okay, so the force equilibrium is beautifully satisfied. Now how about if you introduce reaction torsional moment, T reaction, and then here we can easily conclude that TR, then TR is what? TR is equal to 0. Isn't it, right? How about rotation? How about rotation? So let's say according to this coordinate system, so I want to define the displacement field. Let's say rotation, I want to call this a theta. Say this is my rotation field. So the x directions, and because of the boundary condition A, B, C, D. Let's define a rotation, angle theta. And because this is boundary at point A, so we can consider the rotation is equal to 0. And point B, we have rotation theta B, and C, we must have theta C, and D, we must have theta D. Isn't it right? So this is end displacement, okay? Like nodal displacement, nodal rotation, like in one-dimensional problem. Then how do you calculate the angle of twist? The angle of twist of BC segment is equal to theta C minus theta B. Okay. And how about the angle of twist of CD segment? CD segment is equal to theta D minus theta C. Is it clear? Okay. For example, in the case of unidirectional problem, let's say we denote the nodal displacement by UD and the UC and the UB, isn't it? Here the elongation of BC segment was calculated as what? UC minus UB. The elongation of CD segment was calculated as what? UD minus UC. Is it clear? Okay. This is compatibility. Is it clear? Okay. And then how do you calculate angle of twist here? Good, very good. So angle of twist of the total angle of twist. What I mean, if you want to calculate the end rotation, the theta at point D is equal to what? Is equal to if you look at here, is equal to the angle of twist phi CD plus theta C. And then further we can look at here, theta C is given by the phi BC plus theta B. Let's plug in here. Then angle of twist for each part plus theta B. Okay. And how about the angle of twist for AB? By the same logic, we can do phi CD plus phi BC plus phi AB segment plus angle the nodal rotation of point A. But because of boundary condition, it is equal to 0. And the torsional moment of AB segment is what? AB segment, because of this force equilibrium, is equal to 0. That is equal to 0. That's why end rotation is simply the sum of the two angle of twist of segment BC and segment CD. That's how you can calculate. Is it clear? Okay. Alright, so let's revisit the information of stress and strain. So we already defined the sign convention of shear stress and shear strain, right? So if we have a traction on the positive side in the positive direction of the surface, then we want to call this is positive, the shear stress. This is positive. And then to shear strain 2, and this is positive shear strain. So let's say initially we have a square, and if it deforms to this diamond, then we call it the positive shear strain. Okay, now let's talk about the different stress components depending on the observation direction. So let's talk about this situation. So this is the, okay, if you look at the surface of the member, so if you have a surface of the member, I have shear stress. Okay, let's look at the surface. Then I have shear stress development, isn't it? So let's zoom in. So if you zoom in The how? Using my pencil. Okay, so let's consider zoom in. So I'd like to project the stress state into a square, okay, big square. That's what I want to do. So make sure that this stress condition is on a material point at each material point. So I can project the same stress state into, you know, non-zero size of material point. So I'd like to project the stress state into a big square, okay, big square, so that we can manipulate. All right, so we have constant shear traction tau and tau here. By the definition, we have pure shear stress condition. Let's say I wanna denote here. Let's say length, the height is equal to d, and we want to consider an inclined surface. Here is given by angle theta, and we want to observe what happened in this direction. Okay, the angle is also theta. And then because we love Cartesian coordinate system, so if we, you know, if we inclined our viewpoint like this, okay, according to this angle, then we may have normal stress component sigma theta, and if you want to use, you know, this inclined Cartesian coordinate system, we must have the shear stress tau theta, isn't it right? So then how do you obtain the normal stress on that surface and shear stress on that surface? Let's check the force equilibrium for this small segment. Because, you know, the whole structure is on the force equilibrium, then the small part of my structure, this is also in a force equilibrium. So if you project the stress state into, you know, not small segment, and this part should be also in force equilibrium. But if you check also a part of this small one, for this small triangle, this triangle part should be also in force equilibrium, isn't it right? This is a good consequence. Okay, so let's check the force equilibrium. Sum of all the forces. To check the force equilibrium, first I need to introduce a coordinate system. By the way, let me change the color to the black. So x and y. The sum of all the forces in the horizontal direction should be equal to 0. Okay, so let's collect all the forces. So first we have this horizontal component here. So I have traction, but this traction is the left hand direction. That's why it's sinus minus. The traction, the unit of traction is force per area. That's why we need to consider its thickness T, and what is the length of this acting area. Then how do you calculate the length? The length is what? The length is what? D times tangent theta, isn't it right? D times tangent theta. Okay, this is the first one. Now how about second one? So we have this component plus sigma theta, and then its acting area, the thickness, and its acting area is here. So how do you calculate this acting area? This length times cosine theta is equal to d. So which means this length is what? D over cosine theta, isn't it? And this is the force in this direction. So I need to project this force in the horizontal direction, isn't it? So that's why we need to multiply cosine theta. It's cancelled. Is it clear, right? Okay. And how about the contribution of this guy? And then its direction is that produce negative horizontal component minus tau theta times the thickness, and again the length is what? The cosine theta. Okay. And then we need to consider what? Sine theta, isn't it? Sine theta. T is the thickness. T stands for the thickness, isn't it? So make sure that here the shear stress tau, this is stress, okay? Stress unit. It has stress unit. So look at this here. We want to check the force equilibrium only for forces. This is for only for forces, okay? This is for only for forces. So look at Newton. Please recall Newton's second law. Newton's second law is the sum of all the force vectors. Okay, all the force vectors should be equal to mass times acceleration vectors. So these equations are only for forces, not for traction. But I mean, not for force per some unit area or force per the unit length. It is not, okay? So we are talking about only the forces. That's why we need to, when you check the force equilibrium, you should be careful that the units of all the quantities that we talk about must have the force unit. This is the force per unit area. That's why we need to consider the thickness and the length. Again, the thickness and the length. Thickness and the length. Is it clear? Okay. And the force equilibrium in the vertical direction too. That should be equal to 0, okay? The force equilibrium in the horizontal direction should be equal to 0. And then we do the force equilibrium in the vertical direction too. By the same logic, we have one vertical component minus tau times the thickness, and then the length is equal to d. Length is equal to d. Plus, and then we have this point, sigma theta times thickness, and then the length d cosine theta, and then here we have to consider sine theta, and also we need to consider the shear stress tau theta, and then thickness d cosine theta. This guy we need to consider cosine theta. Cancel. Should be equal to 0. So what you have to check here carefully is what? So we have common factors. T times thickness times the length. Thickness times the length. Thickness times the length. In these two equations. Which means this consideration doesn't matter for the specific thickness of the member and specific size of the member. Alright? So we have two equations and the two unknowns. What I mean, sigma theta and tau theta. That's why we can solve this equation. So once you solve this equation, we can obtain the information of the normal stress in the arbitrary directions. The normal stress in the arbitrary direction is given by this equation, the shear stress and the angle where we observe the normal stress component. And then this is shear stress. For instance, if angle is equal to 0, then we have normal. If theta is equal to 0, normal stress is equal to 0. Okay, there's no normal stress. So we have, if we put theta is equal to 0, I have just tau. Okay, tau. Okay, this is on this side is angle theta is equal to 0. Now how about this side? This side is the theta is 90 degrees, isn't it, right? If we put 90 degrees, sine pi is equal to 0. But let's put pi over 2. The pi over 2 is what? Pi over 2. So pi over 2 cosine pi is -1. Okay, this is a local definition of my Cartesian coordinate system. This is positive direction and this is positive direction. And on this side, and this is my positive direction and this is my positive direction. But with respect to this coordinate direction, this is what? The opposite side is minus. That's why we have, if you put pi over 2 cosine pi, that's minus tau. Okay, but in that direction. And this is what? That direction is what also again here. Okay, and then we must have pi. Theta is 3 over 2 pi. Okay, so let's consider let's consider the 45 degrees difference. If you want to observe the shear stress on this side, okay, if you do on this side, we must have the coordinate system like this. This is a local Cartesian system. Then surprisingly, sigma theta is what? Tau times sine 2 times pi over 4. This is pi over 2. This is tau. And then how about tau theta? Tau theta is equal to 0 in 45 degrees. And then in 45 degrees, this is what happened. And then we can repeat this operation. What you can obtain is normal stress is equal to tau and tau. And then we have compressive normal stress, but whose magnitude is equal to tau. This is a change of the shear stress and normal stress depending on the observation directions that governed by these equations. Actually, we already discussed how the normal stress and the shear stress change by the observation angle in chapter 2, isn't it, right? In the uniaxial structural system, so we consider an inclined cross section, we calculate the normal stress and shear stress. Okay, so that one, that direction corresponds to theta is what? Theta is equal to 45 degrees. And then this pi over 4. And how about this direction? Theta is what? In this direction, isn't it, right? So this is 90 degrees plus 45. Jungu, why tau? Look, here this tau, it represents only its magnitude, the magnitude of normal stress. So we have normal stress. The magnitude of normal stress at theta is 45 degrees. Is equal to, by chance, the magnitude of shear stress in the reference plane. Okay? Good. And then this direction is what? This direction identified by this normal. This direction corresponds to 135 degrees. And then how about this direction? This direction is what? Theta is 180 degrees plus 45 degrees. And this direction is 306 degrees minus 45 degrees. Is it clear? Okay, so let's consider torsional moment. So what according to our discussion here, if you look at this, the magnitude of shear stress is changing, and also normal stress is changing by the observation direction, isn't it right? So for example, even if we have pure shear state, but if you observe the stress state in this 45 degrees, we have tension. We have tension in this direction. We have compression in this direction. So let's say we have a structure made of chalk or concrete. Then where are we gonna have a crack? Because concrete is weaker in tension. That's why our crack should develop in this direction, isn't it right? For example, we have circular members and we pure, it is subject to torsional moment like this. Because of torsional moment, and we have tension, crack would develop in these directions. So if you combine all these, the potential, tensile crack development, we have failure surface, so-called helical failure surface. Look at this. We have helical failure surface. Actually, I did this experiment in my office in 2006, 2 years after I joined Korea University. And we simulated my test using a computational method that we developed. So we were able to obtain this helical crack surface. I did it just for fun. Okay, so now let's talk about the relation between the shear stress and then the shear strain development in pure shear deformation. Let's imagine that I have a material point subjected to pure shear condition. So with respect to this coordinate system, if you project the shear stress, a pure shear stress condition into a square, then we can consider the shear stress is equivalent to that we have shear traction on these edges, isn't it right? And then because of this shear stress, and then this block, this square would deform like this, like a diamond, isn't it? So if you rearrange, if you simplify this configuration, initially I have a square, and then if you have shear deformation, and this square becomes a parallelogram, like a diamond. If you support this diamond on edge, it becomes a parallelogram. Okay? And by definition, this is called shear strain gamma. Shear strain gamma. Because if this is a square, and I want to call this, I want to measure this h by h. And this is a shear strain. This is what? How much is it? This is equal to gamma times h, isn't it? So let's try to measure the length change. So initially I have what? This initial length is what? This initial length, let's say L naught. The L naught is equal to square root of 2h. Isn't it right? Square root of 2h. And how about the length after deformation? The length after deformation is what? The length after deformation is, we can use Pythagorean theorem. So L is equal to square root of 2. The height is equal to h square plus And then we need the bottom length, isn't it right? This is h plus gamma h squared. So many, because gamma is too small, I can use, yes, because we are talking about small strain, gamma, yes. This is how you define radian, isn't it? That's the definition of radian. And this is equal to h, and then 1 plus, what? 1 plus gamma squared. Okay, so let's try to measure the strain for this length. So the maximum strain is measured as what? L minus L naught divided by L naught. The procedure is given in my lecture note. So this is L naught. So make sure that this H is cancelled from both sides. That's why we have this equation. Okay, so here H times L plus gamma square minus square 2H, and then square 2H cancels. And then again, this is equal to 2 plus 2 gamma plus gamma square minus square 2. Make sure that gamma is small. And how about gamma square? Gamma is small. Gamma square is very small, right? Very small. So we can drop because this is very small. And then we have 2 here. Also cancels. It cancels. That's why it becomes 1 plus gamma minus 1. So let's use the Taylor expansion now. If you use Taylor expansion, so if you approximate square root 1 plus gamma with respect to, gamma is equal to 1. You know what's Taylor expansion, right? So 1 plus gamma is equal to, when gamma is equal to 1, so 1. And then we take the derivative. Is a half, and then 1 plus gamma minus a half. This is derivative of this. And then we multiply linear term of gamma. And the gamma, now we want to consider the gamma is equal to 0. That's why it cancels, it becomes a half. 1 plus a half gamma minus 1. Cancel. So finally, the maximum normal strain for this configuration, the maximum normal strain is equal to a half of gamma. And what's the relation for the maximum normal strain? So for the maximum normal strain, how do you calculate the maximum normal strain? Say if I have a square, if you observe the maximum normal strain, then initially we have shear stress, but if you observe the same same stress state in the 45 degrees, we have tensile stress and the compressive stress. So we can calculate the strain development in this direction by using Poisson's equation. So epsilon max is what? It's caused by strain caused by the positive tensile stress, and then the strain caused by the negative tensile stress, isn't it? So by the definition, this is equal to normal stress tau, so its magnitude is equal to tau divided by elastic modulus, and then we have what? The shear stress here plus contractive, because that produce compressive strain, that produce tensile stress, plus Poisson's ratio tau elastic modulus. This is equal to 1 plus nu Poisson's ratio tau e. And how about shear modulus? By the definition, if you understand constitutive model, tau divided by shear modulus, let's let them equal. So finally we have this equation. If you let them equal to each other, then we can obtain the relation between the shear modulus and then elastic modulus. Here the shear modulus is not independent of elastic modulus. Okay, so if you have elastic modulus and then the Poisson's ratio, so we can obtain the shear modulus for the linear elasticity. Okay, and for isotropic linear elasticity. Isotropic linear elasticity. Isotropic means the material behavior is same in any direction. Okay, wherever we measure the material response, we have same elastic response. This is called isotropic. But if you consider non-isotropic linear elasticity, in that case, the shear modulus should be determined separately. Only for if you have isotropic linear elasticity, once we have elastic modulus and Poisson's ratio, we can determine the shear modulus. In 우리말, isotropic linear elasticity, in 우리말 we call 등방 선형 탄성. So here 등방 means isotropic. Any questions? Okay, so now let's consider a situation that where we transmit a power by using circular shaft. So here the power is defined as the rate at which work is done. The power is defined by torsional moment and then the angular velocity. Here angular velocity is defined by the frequency times 2 pi. Okay, frequency times 2 pi, because how do you define the frequency? Frequency is 1 over the period, isn't it, right? 1 over period. That's why the angular velocity can be defined by 2 pi times the frequency. And then if you define so-called RPM, revolution per minute, if you look at your car, you can see the RPM of your engine, that RPM, revolution per minute. Then the RPM defines the number of revolution per 60 seconds, That's why we can define it this way, per minute, 60 seconds. So number of revolution and divided by 60. Okay? Alright, so next subject is statically indeterminate torsional members. Okay, well, let's imagine this problem. So we already solved a similar problem in uniaxial loaded member, isn't it, right? So let's consider this problem. I have two members, so member 1 and member 2. Member 1 and the member 2. Okay, so first we have to introduce a coordinate system x, and then let's imagine the displacement field. So x, I want to imagine the displacement angle theta. This is point A and point B. Say point A and point B. So point A is what? Support. So rotation should be equal to 0, isn't it, right? Rotation is equal to A is equal to 0. At point B, we must have non-zero rotation. And then because there's no change in cross-section, the change of nodal rotation and change of rotation should be linear. We have theta B. Isn't it, right? Okay. So now, by the way, we forgot we have external force T, TB. Okay. And then let's consider, let's try to measure the angle of twist for bar 1. So how do you measure the angle of twist for bar 1? Angle of twist for bar 1 is what? It is equal to theta B minus theta A, isn't it right? But here theta A is support. That's why it is equal to 0. It is equal to theta B. And the angle of twist of bar 2 is also theta B by the same logic. Once I have angle of twist for theta 1, can we calculate the internal torsional moment for bar 1? Yes, we can do that. So length L, the shear modulus of part 1, and the polar moment of inertia of part 1. And then we have to multiply angle of twist of bar 1. The angle of twist for bar 1 is what? Now it is equal to nodal displacement theta B. And then how about here? The internal torsional moment of bar 2, L, shear modulus of bar 2, and the polar moment of inertia of bar 2, theta P. Is it clear, right? Okay, so now what's the next step? The next step is we need to check the force equilibrium. So where do you want to check the force equilibrium? So we want to check the force equilibrium. Maybe best part is here, right? Let's check the force equilibrium. Look at this. Because we use the right hand rule. Look at it. This guy is internal torsional moment. Because this is internal, it should be always in self-equilibrium. So let's say this is torsional moment T. Angle 1 and angle 2 각각 뭔가요? Where is the angle 1 and angle 2? So phi1 is angle of twist. Phi1 is angle of twist of bar 1. The phi2 is angle of twist of bar 2. Separately, okay? Like elongation in uniaxially loaded members. So if they are internal torsional moment, they should be, you need to consider always in the couple. Is it clear, right? For example, okay, let's check the force equilibrium for this part. If you check the force equilibrium for this part, and then here, because we use right hand rule, this is positive internal torsional moment, isn't it right? So we have two positive internal torsional moment, T1 and T2. And then it is combined with the external torsional moment, TB. So let's check the force equilibrium. Sum of all the forces. When we check the force equilibrium, torsional moment is equal to 0. Double-headed arrow. This is equal to TB minus T1 minus T2. They should be equal to 0. But because of this, G1 IP1 L theta B plus G2 polar momentum inertia of 2 L theta B is equal to external torsional moment TB. So can we calculate the end rotation? Yes, very easily, right? the external torsional moment applied to point B is divided by the stiffness of bar 1 and bar 2. This is kind of parallel coupling. Okay? Okay, let's follow the displacement compatibility. So if you follow the procedure given in textbook, look at this. And then first, we have to decompose the structural system into two. For example, system 1, as given in the textbook, so we want to consider only the bar 1. Okay, bar 1. Okay, the bar 1. And then system 2. So we want to consider tube 1, tube 2. Let's say tube 2. Okay, and then I want to consider how to say, let's imagine that it is subjected to T naught. And then this guy is subjected to what? Please consider the force equilibrium. If you superpose these two structural systems, it should be equal to what? T naught should be equal to TB, isn't it? That's why it should be equal to TB minus T naught. Is it clear? See, here T naught is unknown. Well, I don't know that, okay? I don't know that. But what we know is if you superpose T naught and TB minus T naught is equal to TB, that reproduce the original condition. Now we can solve the individual system separately. Okay, so let's try to calculate theta B of system 1 and the theta B of system 2. Alright, so how do you calculate this? Because as you understand, this is angle of twist is equal to end rotation. We already know the information. The theta B of system 1 is equal to the length and then shear modulus of part 1 and the polar moment of inertia of part 1, and then we need to consider torsional moment T naught. Theta B2 is equal to what? L and then 2 IP of part 2 TB minus T naught. So make sure that because of displacement compatibility, theta B of part 1 should be equal to theta B of part 2. This is displacement compatibility. So let them to be equal to each other. So LG1 of IP1 T naught is equal to, so if you move this part on the other side, plus LG2 IP of 2 T naught is equal to the remaining part. Then we can calculate T naught. So if you put the T naught into here, we can obtain the end rotation. You must have the same result. Is it clear? So you can follow the procedure given in your textbook, or you can follow the procedure that I suggest. So either one is okay. Any questions? So now let's talk about the strain energy. The issue of strain energy is always same. Say I have force and displacement, or the member level in the uniaxial loaded member, the internal forces of elongation, or the stress and strain. Okay, so on each level, this is flow of our analysis. or we can go in this way. So on each level we have energy pair, and that forms the external energy that I already explained you, and that forms energy density, and that forms internal energy, the member level. Is it clear? So I told you that this is what? This is so if you plot the angle of twist and the internal torsional moment for linear elasticity, there is a straight line. I told you that the area under the curve is called deformation energy. Deformation energy, is it right? And then here, what is the control variable? The control variable is not the torsional moment, and then the angle of twist. This is control variable. But for the linear elasticity, the area, the upper area is equal to the lower area. That's why here, if you compare the value, they are the same. But the area, the upper area is called U star. So I told you that U is called deformation energy. And then here the control variable is what? U, here the angle of twist. And then the upper part is called complementary deformation energy. Complementary. So make sure that here the control variable is internal torsional moment. But only for the linear elasticity, the magnitude is the same. Only for the linear elasticity. But if you have a nonlinear behavior, for example, it looks like this. So obviously, you can easily understand that they are not the same. This is U and the U star. Is it clear? Okay, now let's talk about torsion of non-circular members. Okay, let's look at what's going to happen if you have torsional behavior in non-circular section. Look. Okay, let me see the camera. Alright, so let's look at this camera. I have my small wallet, okay? So let's try to twist my small wallet. I don't know if you look at it clearly. Alright, look at this. I'd like to show you the cross section. So if I twist my small wallet, okay, look, if I twist it, then can you see the length change here? This corner moves forward and this corner moves backward, isn't it right? So generally speaking, if you consider the arbitrary cross section rather than the circular section, we have length change in the longitudinal direction. A part is move forward and the other part is move backward, and we call it warping. Warping displacement. And this warping displacement makes problem very, very complicated. That's why we cannot use this pure torsional moment formula. We cannot use pure torsional moment formula for arbitrary cross sections. So we cannot do it. Okay, we cannot do it. So to prevent this warping torsional moment, what do we do in reality? So we need to put a diaphragm. For example, let's consider a channel section. So only cross section that there is no warping is circular section. Okay, let's consider this channel section here. If you consider this channel section, so as we showed in as we saw in the this lecture note, if it is subjected to the torsional moment, we have warping. So to prevent warping, so what we do is we install, you know, a diaphragm here, strong diaphragm. Okay, to prevent warping. This is called diaphragm in 우리말. Diaphragm to prevent warping. So only circular sections don't have any warping displacement. And the elliptic section too. Elliptic section also has diaphragm. And you don't have to memorize these formulas. These informations are advanced subjects. So I'd like to skip it. And the triangular sections too, rectangular sections too. Alright, so next week, and we'll talk about thin-walled tube. So let me start my lecture here today. Do you have any questions for what we discussed? Actually, we discussed the torsional members very quickly because the structure, the structure of the knowledge system is very similar to the uniaxially loaded members. That's why we moved very quickly. But if you have any questions, please let me know. Okay. So here, I think you found that most of the information that we discussed are very, very similar to what we discussed in the uniaxially loaded members, isn't it? Right? There is close similarity between these two chapters. We spent significant amount of time to discuss the principles underlining the information given in chapter 2. Huni, in the last example, T1 minus T2 plus T3 is equal to 0. How come AB twisted deformation is equal to 0? Oh, the force equilibrium is equal to, there is no force, okay? There is no additional force, then the twisted deformation at that segment should be equal to 0. No force, okay? No force means no deformation. Unless you introduce the temperature change. In that example, obviously we didn't consider any temperature change, any non-mechanical actions which produce deformation. That's why. Other questions? No questions? Okay. See you next time.